Thank you very much. Thank you for introducing me, and thank you for all organizers. I'm Ryuya Hora, and today's talk is about the colimit of all monomorphisms classify hyperconnected geometric morphisms. So I want to make this talk very simple, and I will talk only about one definition and one theorem, but possibly several propositions. But the only definition is a definition of what I call local state classifier. Local state classifier, which I call LSC, of a category C, is a colimit of all monomorphisms if it exists. So it could be a large colimit. And our main theorem states that every Grothendieck topos has a local state classifier, LSC, and every hyperconnected geometric morphism corresponds to exactly one internal semilattice homomorphism from that LSC xi to omega subobject classifier. And later, I will explain some details and terminology here. So before explaining mathematical content, let me explain some background thing and my original motivation. So one of my original motivation is the open problem posted by William Lawvere. And the question asks, is there a Grothendieck topos for which the number of these quotients is not small? And at the other extreme, could they be parameterized internally as subtoposes are? So this is the question. And here, a quotient of a topos E, here it means a connected geometric morphism from E. It means a geometric morphism is connected if the inverse image functor is fully faithful. That is the definition of connected geometric morphism. And recently, I and my friend Yuki Kamio have proved this open problem and by a very specific topos, that one. But today, I will not talk about the solution of the open problem, but I will talk about hyperconnected geometric morphisms, because this result about hyperconnected geometric morphisms give, in many cases, practical way to actually calculate hyperconnected geometric morphism. And let me explain a little bit more. So when William Lawvere said internal parameterization of subtoposes, he meant the famous bijective correspondence between subtoposes and Lawvere-Tierney topology. And it can be seen something like bijective correspondence between external thing and internal thing, because subtopos is a embedding geometric morphism into that topos, and Lawvere-Tierney topology is a morphism in the topos, so it can be said something like correspondence between external thing and internal thing. And Lawvere's open problem asks about the similar bijective correspondence between connected geometric morphism and something. But in a very restricted sense, I and Yuki Kamio proved that it is impossible in a very restricted sense. And today I will talk about there is such an internal parameterization for hyperconnected geometric morphism. And I will utilize new internal semilattice in a topos, which I will call local state classifier. So let me start talk about definition and properties of LSC. So first, as I said, the notion of local state classifier of a category is just a colimit of all monomorphisms. By that, I mean from a category C, we can define the category C mono that just have exactly same object as C, but only monomorphism of C. And we can consider the canonical faithful embedding functor, then we can consider the colimit of that large diagram. And the associated cocon is referred to as small xi. So In other words, the notion of local state classifier is just an object xi equipped with a family of morphisms from every other object in the category, such that for every monomorphism like u to x, that diagram commutes. And of course, it should be universal among such data. So maybe this definition looks too kind of transcendental. So let me explain the intuition behind this definition. So first, just imagine take an object x from your category and consider the morphism, the associated morphism small xi, and just imagine taking an element or generalized element x and try to calculate the value of small xi x. Then you can take an arbitrary small subobject that contains the element x. Then, by the definition of local state classifier, because it commutes with every monomorphism, we can construct this commutative diagram. And we have the equality xi ux is equal to xi xx. So this means, this informal explanation means the value of small xi x cannot depend on some global data. I mean, that value can be calculated in arbitrary small taken neighborhood. So by this means, I call it local state classifier. And possibly the most important property is that every Grothendieck topos has a local state classifier. And this is non-trivial. Even though Grothendieck topos has all small colimit, but the definition of local state classifier, the indexing category is large, so the existence of local state classifier is non-trivial. But in my paper, we can actually concretely construct local state classifier. And in particular, the local state classifier of pre-shift topos has a very good description. It can be said a kind of dual to the subobject classifier. So for small category C, the local state classifier of pre-shift topos is a pre-shift of quotient objects of representables. So this is kind of dual because subobject classifier of pre-shift topos is pre-shift of subobjects of representables, which is called SEV. So, and I need to explain how it admits an internal semilattice structure. If a Cartesian closed category, C, has a local state classifier, in particular a topos has it, then LSC admits a canonical internal semilattice structure. Let me explain what it is. So first take a pair of objects from your category, X and Y, and you obtain two morphisms, and one is to xi times xi, and one is to xi. And there is exactly one morphism from xi times xi to xi that makes this diagram commutative for every pair of objects X and Y. And this defines an internal semilattice structure on the object xi. And so far, we've seen three things. First, a local state classifier of category is defined to be just a colimit of all monomorphisms. And every Grothendieck topos has local state classifier. And if a Cartesian closed category, in particular a topos, has a local state classifier, then xi has a semilattice structure. So let me state main theorem. But before that, let me recall the notion of hyperconnected geometric morphism. A geometric morphism, E to F, is called hyperconnected if the inverse image functor is fully faithful, which is also called connected geometric morphism, and its counit is monic. There are a lot of well-known equivalent definitions, but today I adopt this definition. And possibly the most famous example is topological group 1. For topological group G, there is an inclusion factor from continuous action topos of G to the pre-shift topos over the underlying discrete group G delt. And this fully faithful embedding factor defines a hyperconnected geometric morphism in the opposite way, because this fully faithful embedding factor should become the inverse image part of the geometric morphism. And as shown in the Johnston's paper, it is a part of what's called hyperconnected localic factorization system, which is one of the most important factorization systems of geometric morphism, maybe. And let me state our main theorem. If a topos E has a local state classifier, there is a one-to-one correspondence between hyperconnected geometric morphism from E and internal semilattice homomorphism from Xi to the subobject classifier omega, and internal filters F. So the last part is kind of trivial. It is immediately implied by the general theory of internal semilattice of topos. But I intentionally write it because it is, in practice, in many cases, it's easier to calculate. And it is in the informal duality with the subtopos case, it corresponds to the notion of Grothendieck topology in a dual sense, in the very special case of pre-shift topos. Then let me give a very rough sketch of the correspondence of the first part and the second part. From the first part, from a given hyperconnected geometric morphism from E to F, by our definition, we obtain the monic co-unit. And from this, since we are considering topos, we obtain a family of morphisms, which is just a characteristic morphism. And we can prove that this family of morphism from every object X to omega is cocon under all monomorphism. And by the universality of the colimit, we obtain a morphism from Xi to omega, and we can prove that it is a semilattice homomorphism. And also we can prove that this correspondence is one-to-one correspondence. So let me give some examples of classifications. So first, let me give a trivial example of the category of sets. The local state classifier of the category of set is a singleton. In fact, there are no non-trivial hyperconnected geometric morphisms from set. The only one is equivalence of categories. But this is non-trivial, but we can generalize this to every localic topos. For Grothendieck topos E is localic if and only if its local state classifier is terminal. This is immediate corollary from hyperconnected localic factorization system and my main theorem. I'm happy with that. Yeah. And let me give a toy example. Sorry. Let me give a toy example of the pre-shift topos of directed graphs. For the topos of directed graphs, I mean just a pre-shift topos over the parallel morphism. And the local state classifier of this can be calculated by the proposition that I've mentioned, because this is just pre-shift topos. And it is given by two bouquets. It has one object. I mean one vertex, and two edges. One is labeled by being a loop, and the other one is labeled by not being a loop. And from every graph, we can consider there is associated morphism, graph morphism, small xi, and that small xi sends every vertex to the unique vertex, and every edge to one of the two edges, depending on whether it is loop or not. And there are two hyperconnected geometric morphisms from this topos corresponding to these two internal filters. And let me give another example from a group G, I mean discrete, just a group G, regarded as a one object category. And the local state classifier of this topos, of the topos of right G action, which is just pre-shift topos, is a set of all subgroups. And every small xi sends each element x in the G set X to its stabilizer subgroup. And from this observation, we can prove that every connected geometric morphism from pre-shift G, which is automatically hyperconnected, is induced by a topology on G. And we can actually prove that there is a one-to-one correspondence between hyperconnected geometric morphism from this topos and a good class of topological group structure on the group G. And at the remaining 3 minutes, let me introduce some personal open problems related to this. So first, the obvious one is the existence of the local state classifier. As I said, every Grothendieck topos has a local state classifier. And for finite category C, the finite pre-shift topos, it has a local state classifier. But there is an example of an elementary topos that does not have local state classifier, and this is the example, phi set to Z. And the question is, when does a topos have a local state classifier?
You mean
elementary? I mean elementary topos. And from this observation, without any other reason, this problem seems to be related some boundedness of our base topos. And I'm also curious about the relationship between boundedness and existence of LSC. And the other question is preservation by functor. So to study some categorical structure S, I think it is very usual to study a class of functor that preserves the structure. But I don't have any good class of functors that preserves the local state classifier, so the question is what kind of functor preserves LSC? And although I said that every Grothendieck topos has LSC, but it is not just a shiftification of LSC of pre-shift topos. So, and actually even a shiftification functor, which preserves every monomorphism colimit, even shiftification functor might not preserve LSC, and this functor gives one example of shiftification functor that does not preserve LSC. And the other question is about generalization of LSC. So, as I said, LSC is defined for all category, not necessarily topos. Of course, sometimes it does not exist. So, LSC should be generalized to broader context like enriched category, enriched context or higher context, or possibly we can consider colimit of not all mono, but other class, depending on what we want to study. And we can consider non-Cartesian case. Or I'm also curious about how LSC can be described by internal language of a topos. And finally, let me give the last question. So from a hyperconnected geometric morphism and subtopos, they correspond to internal semilattice homomorphism from xi to omega and omega to omega. So we can compose them. And we got a new hyperconnected geometric morphism. So the last question is, what is this interaction between a hyperconnected geometric morphism and subtopoi? So that's all for problems that I'm curious. Thank you for listening.